Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Dr. Benjamin Nachman from Lawrence Berkeley National Laboratory entitled Reimagining the Exploration of Fundamental Interactions with AI. Dr. Nachman earned his PhD in physics and a PhD minor in statistics from Stanford University in 2016. He then was a Chamberlain postdoctoral fellow in the physics division at Lawrence Berkeley National Laboratory, or LBNL. In 2020, Dr. Nachman became a staff scientist at LBNL, where he leads the Machine Learning for Fundamental Physics group. This group develops, adapts, and deploys machine learning and artificial intelligence to problems in particle, nuclear, and astrophysics. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. At this time, it is my great pleasure to introduce Benjamin Nachman.
Great, thanks so much, Dean, for the opportunity to present this talk, and I'm going to dive right in. All right, so let's get right to it. There's sort of two parts to this title. There's fundamental actions and there's AI. So let me start with the first part. So what do I mean? What do I mean by fundamental interaction? So just so we're all on the same page about kind of the science context for why we're doing all this work, there's theoretical and experimental questions that motivate a deep exploration of the fundamental structure of nature. So what do I mean by that? Well, we know that there are atoms. Atoms are composed of electrons and nuclei. This is sort of obviously like a classical picture of what an atom might look like. The nuclei composed of protons and neutrons. Inside those protons and neutrons are quarks. There's up quarks and down quarks. So as far as we can tell, most of the things around us are made of these three things, these three ingredients: up quarks, down quarks, and electrons. And that's great. We understand that pretty well. But if we look a bit closer, we find that actually there are copies of this up-down electron picture. And in fact, there's a whole another set of ingredients, the charm quark, the strange quark, and the muon, which are basically just heavier versions of these three. And one can construct exotic matter made of these three things, even though it's not like most of the things around us. And in fact, that's not even the end of the story. There's another copy. So there's three copies, and we don't know why there are three copies. So that's kind of weird. In fact, there's more than three copies, which I'll come back to in a second. But there are other interesting questions we don't understand. So like, for instance, if you Google a picture of the neutron, you might find that it's composed of two down quarks and an up quark, and you'll probably see pictures like the left-hand one, where they're arranged in a triangle. But as far as we can tell, actually, they're more like arranged in a line, just the way the orientation of the charges is inside the neutron. And we don't know why that is. That's the neutron dipole moment problem. And as I alluded to, there's actually even more particles altogether. So every particle has an antiparticle. So there are not 9 constituents of matter. There's actually twice as many. And to make things even more complicated, there are even particles we know exist, but we don't know what they are. So there's dark matter, which is a mysterious object that interacts gravitationally. We have no idea what it's made out of. And so all these things together motivate us to ask big questions to get to the bottom of this. Now, how do we start to make progress on answering these questions? So to do that, we perform experiments or conduct surveys. So we want to learn something about nature. Ultimately, that's the goal. And so to do that, we perform experiments. For example, we might build a giant collider. And then the collider might crash particles into each other, and out goes collision debris. And so we need some instrument to be able to measure the outgoing particles, sort of like a microscope, to figure out what exactly happened. And then we need to reconstruct what happened. So a detector might have many subcomponents. So here's a cross-section of the CMS detector at CERN. So particle collisions come into and out of the page, and at the very, where my mouse is on the left-hand side, that's where the protons collide, and out goes some particles, and they fly off in this case, transverse to the collisions, and different particles interact differently with the sub-detectors. So this teal line, for instance, is a muon, interacts with all these different components, and we need to reconstruct the trajectories of, say, the muon, the single muon, from all these different components. A single particle might interact with hundreds or thousands of components, and we need to reconstruct, say, just the momentum of the particle. But then to make progress, we want to put this nature in some context of a theory. So we have a theory, and that theory will have some equations of motion to describe various particle properties. We then can simulate basically the equivalent of an experiment. We can, on a computer, simulate, say, two particles colliding and stuff happening. And then we can also simulate those particles that are flying out interacting with the detector, basically exactly the same virtual version, the digital twin of the detector that actually exists in reality. And then we can apply from that the same kind of reconstruction algorithms as in the actual data. And then inference proceeds by comparing the left-hand side and the right-hand side. And when the result of the theory agrees with what we see in the experiment, we say the theory is correct, basically. So in a few more words, we want to be able to do this comparison. And it's complicated because a given experiment might have, say, thousands, millions, hundreds of millions of readout channels in its detector that might get compressed to, say, tens, hundreds, or thousands of reconstructed particle trajectories. And that is a very high-dimensional space. It's hard for me to even visualize 3 dimensions, nonetheless 10,000 dimensions. So how can I compare these 2 different data sets in, say, 10,000 dimensions? And the answer is we don't. And so instead what we do is we say, let's pick a single dimension in this 10,000 dimensional space, say the mass of some set of particles. That's a single number. So I can summarize the entire, say, collision event by a single number. And I can make, say, a histogram, the frequency of getting a number in a certain range. And then we can make a plot like this as a histogram, say, from the data. We can make the same histogram from the simulation. And now we can make progress. You say we have 2 histograms, and I just want to compare the histograms. And there are simple ways of doing that. And I can change the theory. So say I change the theory, I get a different histogram. Another theory, different histogram. So here I have 3 theories and 3 different histograms. The data are the same. The data are whatever they are. And now I can say, okay, I define some compatibility criteria to say which of these, is the histogram the same as the data, the simulated one the same as the data? And this kind of schematic would be like the compatibility as a function of the theory. And say, okay, that middle one is the most compatible. So that's nature right there. Okay, so that's how this sort of works. And this is how we've been doing, fundamental science for, I don't know, forever, basically. Okay, so that's great. But the really key challenge of what I just said is that we take this really high-dimensional, rich, complex space, thousands, hundreds of dimensions, all these particles and their property, and we compress it down to 1 or a few. And this is fundamentally limiting the utility of these complex data. And so it's calling out for a solution, and the solution, or a solution, is to use AI. And I'm going to use AI and machine learning interchangeably. I'm happy to say later about nuances between the definitions of different words, but more or less these tools are techniques that allow us to automatically identify structures in data. That's ultimately what they're trying to do. And they can directly allow us to compare, say, the data and the theory in the high dimensions without having to first compress it. Now, this is enabling us to do science that was sort of unthinkable before. And it's what's really exciting and what I do for research. So I'll try to give you at least some taste of that in the time I have left. Okay, so now you may ask, well, I've been living in the world for the last years, and I know that there are great tools for doing AI. Hasn't filling your favorite tech company solved this already? I know about ChatGPT and other tools, and it's true that they have made fantastic progress. So in a sense, yes, but in another sense, no. So industry has provided amazing tools, and physicists are definitely using those tools. I make use of all these tools in my research, but we have unique challenges. And so while industry is solving some of our challenges, there are some challenges that we face that industry will likely not solve. And so there's a great need for AI for science research. So basically developing tools specifically tailored for the problems that we face in science, fundamental science, from physics in particular, but science in general. Okay, so let me give you some sense of this. Okay, so here's a fun example. Let's say you want to use ChatGPT, So ChatGPT it's a language model. You can interact with it. It has a text box. You can ask it questions and you can paste in text and it will give you an answer in text. So the core element of ChatGPT is a machine learning architecture called a transformer. And so I'm not going to say what a transformer is in this talk. I'm not going to show any architectures. I'd be very happy to talk about it later. But there are many other lectures that are more qualified to talk about these kind of things. But okay, it uses a transformer. Now, while our data are not exactly a language, it is variable length. And while particles are not like text, they're sort of like, you can imagine, they have some similarities to text. So they're not discrete. Like, so text is discrete. You know, there's like only so many letters. Whereas for us, like the momenta of a particle are continuous. But okay, that's a small difference. And so we also can use transformers in sort of a different way than for language. Like I said, it's not discrete. And there's also differences in that there's no order. So, you know, in text, like the order of the text makes a huge difference. In our collisions, there's no sense in which like particle A came before particle B. They have a different relation, and you can encode that also in a transformer. So we use transformers. That's sort of the state of the art. This is a picture of a collision, the collision debris from the CMS experiment, where the particles are colliding sort of sideways into the page, and out goes all these particles. The yellow lines are particle trajectories, and there's green and blue blobs that correspond to other elements of the detector. And so this is sort of like imagine this is like an essay. You know, we want to describe this using something like ChatGPT. So you can definitely do that. Suitably modified. Like I said, it's not exactly like language. But there's a caveat, and the caveat is that this is a really fun example. So you can open ChatGPT right now. It's a homework assignment. Take your two favorite large numbers and multiply them. Ask it to multiply them, and so it'll tell you, find the product, blah blah blah, and it gives you a number, and therefore the product is blah blah blah. So huge number, okay. And then take out your calculator and plug in those two numbers and check, and you'll find that it's probably not the right. And in fact, you can do this exercise, and it's well known that ChatGPT it gets worse the bigger the numbers are. For very small numbers, it does a fine job because it can just memorize it, and then very high numbers, it gets it wrong. Now, of course, you could say, well, who cares? I mean, I also can't do that in my head. It could just use a calculator. And that's true, but when you're thinking about a model parsing scientific data, it needs to be able to understand about numbers. And numbers are bigger or smaller, they have magnitudes. Some numbers have come before other numbers, they're continuous. And these are all things that are kind of hard for a language model to deal with because inherently language is not like that. And so this is calling out for custom solutions. And I'm just going to briefly describe one solution, not the only one, but something that people in my group have been thinking about. So the way language models work is you have like a sentence, like the sentence at the very top left, 5 trials at pH 7.4. And the way it works is it takes that and turns into tokens. So tokens are the thing that the language model is generating. So tokens could be letters, they could be fragments of sentences or fragments of words. In this case, imagine each of these words is a token or gets encoded as a token. Then you have, normally you'd have like 5 and 7.4 would have their own tokens. But that's where some of the problem comes because you need a lot of tokens, right? Because the numbers are a lot of numbers, they're infinitely many numbers, and they're continuous. And so, one possible idea, which I'll describe in a second, is basically instead of having a different token for every number, have one token for all numbers. Call it num or whatever. And then the way it works is the tokens basically get embedded into an abstract space. And in that space, that's where the model kind of parses them and does some stuff with them. So let's say all numbers get mapped to the same abstract point in the space. And then when the model actually uses it, you just like take that vector in that space and just multiply it by the magnitude of the number. And so in that way, like all the numbers get sent to the same vector, but then 7 would be stretched by a little bit more than 3. And so the model then gets to know that 7 is bigger than 3, and that 6.9 is really close to 7, closer than it is to 3, because the length of that vector is suitably just scaled by a continuous number. So there's like a discrete component, which is the token itself, and then there's the continuous component, which is the length of the vector. And so this is a kind of a pretty simple and elegant idea, and it turns out it works pretty well. So here's just one example. This scientific problem is, say you want to look at exoplanets, and so you're observing some planets and or some spectra to look for the properties of planets rotating around stars. And here, this A1 is one of the parameters of the elliptical rotation, and you want to let's say parse data and infer the value of this based on some data. And all the different, the x-axis here is the true value in this simulated example, and the y-axis is the real value. So you want it to be, or the inferred value. So you want it to be, a one-to-one line here. And the black dashed line that's the right answer. And all these different things here are different encodings. So if you use I'm not going to say what the orange, green, and red are, but they're standard encodings. Basically, you use like a fixed number of tokens. So you basically truncate the number, and you say if it's like 3.7, you have like 3.7, right? So that's like very one standard way of doing it. And you see they work pretty well, but they have these like weird jumps, and they're not always exactly the right answer. And that's exactly what I was talking about, how like they don't know that numbers are continuous, and they have all these jumps. The blue is this new one where you have all of them going to the same one, and then you scale it accordingly. And you see it's sort of continuous and smooth and gets close to the right answer. So this is just one very pretty interesting example where it's actually important that we impose the structure of our problems in the machine learning. Okay. So another example I'm going to give is simulations. This is a huge difference between industry applications of language models and science ones, in particular fundamental physics ones. So there's no generator of essays or cat pictures. There are a lot of cat pictures online, but they're all taken by people unless they're generated by an AI, which has been trained on pictures taken by people. So in contrast, we can simulate basically from the very, very small to the very, very large, all the interactions of particles and interacting with material. So in what I said earlier, basically we can generate data that looks exactly like real data, even presented to an expert. And so that gives us a unique opportunity where we can create tons of synthetic data that have labels, already have labels that have been annotated to say, I know exactly what's in this picture of a collision because I made it. Whereas if you look at the internet, there's tons of pictures of cats and dogs that are just pictures of cats and dogs. And so a language model developed in industry needs to figure out the structure of the data from the data itself. There's no way for us to give it advice other than to hire a bunch of people to label the pictures. Whereas for us, we can generate large numbers of data that are annotated because we generated them. And that gives us a unique opportunity to build models that can do more, or different things at least. Okay, so the industry has to learn the structure of the data. We have these simulations. So like for example, there are tools where I can type in my computer, generate 2 protons colliding and producing electrons. So that's like what this line here is. I'm not even exaggerating. That's like the exact line I would type into this particular generator, and it would generate something like the picture on the right. Okay, I've kind of skipped a few steps, but basically that's what you get. And I can play God basically. I can say, well, actually, what if the electron mass was a little bit different? And I can say, okay, this line at the bottom is exactly, it doesn't matter what the details are. But basically, I can change the electron mass from whatever it is to some other value just for fun, and I can see how does it change the output. And so I can really have this like synthetic playground where I can generate huge numbers of annotated data where I controlled everything because that's kind of the box I live in, and I can use those then for doing new exciting things. Okay, so this means we can generate, like I said, basically infinite labeled shredding data. And so just to give some sense about what we can do with that. So the left-hand side here pictures, these are pictures from some work in high-energy physics where we have a detector simulator. It's called Geant. That's the top row. And we want to emulate it with a generative AI. The generative AI tool is called a GAN. Doesn't matter too much. And basically, we can show the GAN many, many examples from Geant, the physics simulator, where we tell it everything. We know exactly what energies were used, and all the properties of the detector, and the structure and everything. And so the neural network has to learn to mimic that, but gets to know all the structure. And so that allows us to do all sorts of fun things, where we can even condition on physical properties like energy. We can impose energy momentum conservation, and that's sort of the kind of problem we have, which is pretty similar to, but not the same as problems in industry, where like let's say you want to generate pictures of people. So this picture on the right, this is also from a GAN, same kind of generative model. These people don't exist, by the way, and it's very fun. You could spend a lot of time on this website, this person doesn't exist.com, and it will generate pictures basically look like this. But it had to learn from many, many pictures of people on the internet, like what people look like, and then it has to learn their structure. It doesn't know about eyes and ears and noses and all that stuff. It has to learn that directly from the data. In our case, we know everything because we set it up. There's some things we don't know because we set it up. Like we can generate the simulation, so there's some things that are implicit that we didn't explicitly put in, and that's what we want the model to learn. But kind of the setup is something we understand, and so that's really kind of a different and exciting opportunity. Okay. The third example I'm going to give is a little bit more involved, so I'm going to spend a little time on it, which is to say that the ways that we use machine learning sometimes have different requirements in the way they're used in industry. So I'm going to explain what I mean by sculpting. Okay. So one very common task in, say, collider physics is you want to search for new massive particles by taking two particles, smashing them together, using E equals mc squared, get as much energy in one place that you can, turn it into a very massive particle if it exists, and then reconstruct the collision debris and see if there's something new. Okay, so the way we tend to do this is, say you have a picture like this, where there's a histogram. So I have reconstructed some mass of some particles in my detector, and I want to see, is there an excess of events that have a mass at some particular value? And so in like this, the known physics, if there's no new particles at any given mass, there'd be the orange histogram, so some kind of like featureless spectrum. But if there's a new particle that has a particular mass, at that mass value, there'll be some excess of events. There'll be some events, because sometimes when I collide the particles, I get that particle produced. And so that would be like the green here. And so what I'm looking for in my data, in the spectrum, is, say, something that looks like this. So there's going to be like, ideally to be a line with a bump over some smoothly falling background. And if I see this, I get really excited. And this is what we see, see in the data. And the way we do this is you want to ask, how significant is that bump? Okay, so we might like fit some function to the data, and then ask, how significant is the bump over the expectation that there's no features in this spectrum. And if the data are unlikely given this, kind of smooth assumption, then we get really excited. We start pre-booking our tickets to Stockholm and stuff like that. That's kind of a very simple idea. But now, where does machine learning play a role in this search? And the idea is that usually we have more than just the mass feature. So in the kind of standard classical way, like I said, you compress the whole, say, event to one number, just the mass feature. But we actually have access to way more information. And so in practice, we have lots of features. And so we can use machine learning on all those features. We can use the mass dimension to do the bump hunt, to look for the excess. But we can use all these other dimensions in order to, say, train some model, machine learning model, to enhance the presence of this signal, basically to make the background go down, but keep the signal the same. So we do that by training a classifier, for example, using some simulations. And we get, the classifier output might look like this, where it's very good at separating the signal in green and the background in orange. And then we might say, okay, I'm going to make a threshold on the classifier and say, toss all the events for which the classifier thinks it's not a signal. And if you do that, the background now goes down. I have fewer background events because most of the background doesn't pass my selection. And the signal basically stays the same because everything to the right is still basically signal. And so this is the picture I would get. So the background goes down, the signal goes up, and so the signal is now a bigger bump on the background, and it's easier to see and it's more significant. So this would be great if I saw this. Background goes down, signal stays the same, the bump grows relatively bigger, and this increases the signal to noise, and makes it more more effective. We can find the signal more significantly with more confidence, and we can also find it with fewer events. So this is the ideal case, but this is not how it usually works in practice. Okay, so in reality, you train this classifier, you make a cut, and what happens is that the background doesn't just go down, it deforms. And so, and the reason is because the classifier, the AI is smart. Basically, you say, distinguish signal and background. And even if you don't give it feature one, the mass dimension, it can infer that from all the other features and say, you told me you're looking for a signal at a particular value. I will only take events that have a mass at that value. And so what happens is it basically just sculpts the background to look like the signal, even if there's no signal. And that's a problem because it's very hard to find a bump on top of a bump. That's basically like rule number one of bump hunting, is you can't find bumps on top of bumps, bumps on top of bumps. Okay, so it's not basically this is not fittable, and so we're in trouble. Okay, and so we can't just take the AI tools out of the box. Basically, that's the punchline. In the ideal case, you use the say a neural network, it makes the background go down, doesn't change the signal, but in reality, the background goes down and deforms. So that's a problem. Okay, so here is where the solutions come in. So one possible solution is to construct a classifier, so a neural network model, that actually knows about feature one. And it knows about it in a way that basically makes it independent of feature one. So you say, I want you to be able to distinguish, say, the signal and the background, but I want you to do that in such a way that your result is independent of feature one. And it's not good enough just to not give it feature one. You could just say, well, don't give it feature one. Like I said, the neural network is smart. It will infer feature one from all the other stuff you give it. And so this requires building new tools that either change the structure of the neural network or change the way it's trained using physical insight. Okay, and this is a very complicated picture. So I'm going to spend a few minutes on it. So, so here, the left-hand side is this is a real example. It's all in simulation, but it's a real example in the sense that these are real simulations of particle collisions. So left-hand side, this is a histogram of the mass of some reconstructed particles, and the red is a background. So this is just generic quark and gluons that are scattering and producing sprays of particles. And the black here is the production of very fast moving W bosons. So the W boson is a particle that's like the photon. It's heavier and charged, electrically charged. And usually W bosons are not moving that fast when they're produced. But if there's some new stuff, they may be moving very fast. And so this is what they would look like. And you see there's a bump somewhere. And it's a bump around the mass of the W boson, which is about 80 in these units. So it's like 80 times the mass of the proton, roughly. And so this is what we're looking for, this bump on top of the background. Now, the way the left-hand side is shown, it's shown in such a way that the black has the same integral as the red, the same number of events, but in practice, if there are any of these fast-moving W bosons, they're a tiny, tiny fraction of the total. So this problem would be very easy, but in fact, there are almost no fast-moving W bosons, and so it would be a really tiny fraction. Okay, so let's say I train a classifier using the other features of these events to distinguish the black and the red, and then I make a cut. So if you do that and then look at the background spectrum, that's the right-hand side. So first, let me talk about the black histogram. The black histogram on the right-hand side looks a lot like the black histogram on the left-hand side, which is confusing because the left-hand side is signal and the right-hand side is background. So the right-hand side is you take the background, you make a cut, and it basically just sculpts the background to look exactly like the signal. So that black is exactly the problem I was talking about. So the right-hand side is no signal, just background. And basically the classifier has just made all the background events look like signal events. And so that bump is not fittable. I can't fit a bump on top of a bump, so I'd have to give up. In contrast, all those colored lines here, they correspond to custom-made neural networks or neural network training protocols that make the classifier independent of the mass. And so they all either independent or dependent in a way that allows you to still fit a spectrum. And so you can see that all these other spectrum, the colored ones, nothing magical happens at 80, right? They just kind of, they have some distribution that's kind of featureless. And so that's exactly what we want. We want distributions that remain featureless after making the threshold. So they reduce the background, they leave the signal untouched, and they're also fittable. So the fittable is a new requirement, and that's where we, if physicists, have come in to solve this problem for us. Okay, so that's at least a partial solution to this problem. And it actually, as I've pitched it here, it sort of seems kind of unrelated to industry and society, but actually turns out it's very much related. So there's a problem that people in AI research care a lot about, or at least should care about, and it's called fairness. And the idea is that, let's say you train a classifier to screen resumes of people applying for jobs, and you don't want it to indirectly learn things, the protected features like age, race, ethnicity, etc. So this is exactly the same problem. Basically, we want to train a classifier, and the protected feature is the mass, whereas they want to train a classifier, and the protected feature is, say, like age. Now, there are some differences. So in particular, our feature is continuous, whereas those features tend to be discrete. But there are fascinating connections where we basically independently, coming at this problem, we've developed kind of slightly different solutions because our requirements are different. But this connection, I think, is pretty exciting to explore in the future. Okay. All right, so I'm then going to spend the last part of my presentation, the next 15 minutes or so, talking about going beyond simulation. So everything I've said so far is how we could couple simulations with data to do inference by taking advantage of all the information available. And that is a big part of AI for science, and in particular AI for fundamental physics. But it's not the only feature. And so our simulations are super excellent. I mean, really amazingly excellent. But there are some good reasons to try to reduce our dependence on them sometimes. And one really obvious reason, super important reason to reduce our dependence is if there's something that is not in the simulations. So say you're looking for something new. Well, if it's looking for something new, it's not going to be in the simulations unless you put it there. And if you don't know what you're looking for, then you don't know how to put it in the simulations. And so this is what I'm going to call anomaly detection. So anomaly detection is looking for unforeseen things. And so there are simulations, they can help us, but they can't do everything for us because by definition, I don't know how to simulate the stuff I'm looking for. Okay, and so this is the critical application of anomaly detection. And I want to briefly highlight how anomalies that we care about are often different than anomalies industry cares about. So in industry, people often care about what are called point anomalies. A point anomaly is you see a single example and you say, that is weird. So for example, you're walking around, you look up in the sky and there's a pig that's flying around. Okay, you're going to see the single pig and say, okay, that's weird. It's an anomaly. Whereas in contrast, a group anomaly is one in which no single example is weird. It's only in context that it's weird. So let's say, you're walking around and there's like a bunch of pigs around. I guess if you're in a place that there's usually pigs, like at a farm. And let's say there's like a few more pigs than usual. In that spot in the barn. So that could also be an anomaly. And no one pig is weird, or I can't say which of the pigs is the weird one. But let's say there's more than usual. Well, that requires me to know what's usual. And so the kind of conditions and requirements for these different kinds of anomalies are just different. And nowadays, at least in particle physics, most of the anomalies we care about are the group anomaly kind. So let me give you some specific examples. So, for example, the Higgs boson was discovered almost a decade ago, and it won the Nobel Prize. The Higgs boson is basically the last fundamental particle that is supposed to. We already know about it, and it exists, and we found it. And it was found by looking as a bump hunt. So we were looking for the Higgs boson decays to pairs of photons. We reconstructed photon pairs, we found this bump right here in the middle. And so no one event is a Higgs boson. We can't tell. But there's this population of events, near this particular mass, which and there are more than we'd expect. And so that's why we say there's a Higgs boson. And this is in contrast to, for instance, the discovery of the positron, possibly the last time that a point anomaly was used for discovery in particle physics. So the positron was discovered over 100 years ago. And a single event, basically looks like a charged particle that's bending the wrong way. And so that is just not possible. And so the single image of a charged particle bending the wrong way in a magnetic field says there's a fundamental particle which has a charge opposite of the electron. So thus the positron, right? And so a single event was here, that's a point anomaly. In this case, I can't tell you which event is a Higgs event. Okay, that's a group anomaly. And so we need tools to find group anomalies. Okay, now there are a lot of AI tools for doing anomaly detection. This is sort of big business. You can imagine it's super important for people to find weird stuff. And the different kinds of approaches are characterized by what information you give the AI when you train it. And I like to connect sort of the physics assumption to what information you're giving the model. So most machine learning that we do is supervised. Supervised means I give the model examples of of images, say, and I tell it what's in the image. So it has to learn to associate the input data with the label you tell it. So say signal or background or cat or dog. Those are the labels. But for anomaly detection, we often don't have labels because I don't know what I'm looking for in particular. I'm looking for something weird. Okay. And so I don't have full label information. I have either no or noisy or partial labels. And the question is, can I still do science with that information? And the answer is yes. Okay, so so one approach is to do things unsupervised. That means I have no labels at all. And the goal of these methods, roughly speaking, is to look for things that are rare. And so the way they do that is they say, let's say I could learn the likelihood of my data. So I say, like, for a given event, I can say, like, what's the likelihood of this event happening? And one strategy of doing that is to build what's called an autoencoder. So an autoencoder is a tool that it's a compression algorithm. So you take your data, you compress it, and you uncompress it. And the idea is that you tell this model, I want the compressed and uncompressed, say, image to be close to the original. That is to say, I want the compression to have worked. And if the model is doing a good job, then the events that are very well compressed and uncompressed are ones that are common, because a compression algorithm should allocate most of its capacity to things that are common, and it'll be very bad at things that are rare, because it doesn't get penalized that much for them. And so one strategy for doing anomaly detection is to take your data, compress it, uncompress it, and compare it to the original. And if the original and the compressed, uncompressed thing is very far apart, probably it's rare. And so that's a strategy where I didn't have to tell it, event by event, is it a signal or background. I just say, go find me things that are rare, and it can return things that are rare. So that's one strategy. Another strategy is where you might have some information, and typically you have some information about the background, even if you don't know what the signal is. So imagine I have a way of generating two data sets, one that has little or no signal, and one that has possibly some signal. So then I know something about the background from the one that has almost no signal, and I can play these two data sets off each other. And that allows me to look for something, even if I don't know exactly what I'm looking for. All I know is something about the background. And so here, it's called noisy labels because I have labels in the sense that I have my background dominated sample. That's like a label of just background, but it's noisy because it still might be a little bit of signal. And I have my little bit of signal sample, which is I call signal, but it's actually mostly background. And so I can then proceed that way. And so here, just as a sort of small table. So for unsupervised, the new stuff is rare if it exists. And if it's weakly supervised, then I'm thinking the signal doesn't have to be rare, but it's more likely than a reference. And so those are the assumptions. And for unsupervised, the main drawback of rare is that rare depends on your point of view. Depending on how you're looking at the data, rare might mean different things. Whereas in the weakly supervised case, you don't have that problem, but you do need to have these two data sets, one that to play them off each other. Okay, so I'm going to just walk through one example in this rare case, or not the two sample case. And I've shown this picture before, so we've kind of been primed to think about it. So doing a bump hunt is very much in this category of playing samples off ech other. So let's say I don't know what the new stuff is, but I think it might be localized somewhere, say in some mass dimension. So I can generate noisy labels by saying I look at data near the wherever the new stuff is, and I look at data that's away from that but close. These allow me to get my two samples. So in the one that's away from the signal, those data have basically no signal in them. It's just background. And then the one that's where the signal is, that is still mostly background, but has a little bit of signal possibly. And I can play these two data sets off each other and see if I can find something new by using all the other features that are available to me, just like before. Except now I don't have to know anything about the signal except where it is in this one dimension. And if I don't know where that is, I can also scan over different values. And so now instead of training a classifier to distinguish background from signal, I'm training a classifier, say, to distinguish the signal-like events from background-like events. And as long as there's nothing else that distinguishes the kind of events, then this procedure is very effective at finding signal events without pre-specifying what the signal is. And this kind of tool can be used in lots of scenarios. So at colliders, for example, you might look for these new massive particles. So for example, the picture on the left is a schematic where you have, say, protons colliding. They make some new question mark particle. The question mark particle decays into sprays of particles called jets. I can reconstruct the jets to get an invariant mass. That allows me to make the mass-like variable, and I can use all the radiation pattern within the jets to do the classifying. The picture on the right is a real event from the Atlas experiment where the particles collide into and out of the page, and this is a cross-section, and you're seeing different elements of the detector. The colored lines are charged particle trajectories, and the green and red blobs are energy deposits in calorimeters. And question mark, one could ask, is this the question mark particle? And I can use all the complicated distribution of charged particle trajectories and energy blobs to figure out is something weird without specifying what the question mark particle is to start with. Okay, but this actually can be used in many different scenarios, not just in collider physics. And the example I'm going to give here is applying this method to a totally different data set. So the example here, just to give a sense of the breadth of these kind of tools, is looking for objects that are called stellar streams. So a stellar stream is a remnant of a protogalaxy that's been ripped apart by the Milky Way's gravity. So basically, imagine you have a little blob that over time has been kind of ripped apart. It's in the Milky Way, but it's been kind of like deformed by the gravitational potential of the Milky Way. And these things are super interesting because they tell us about, well, they might tell you about the evolution of the Milky Way. I'm particularly interested in them because they tell you about the distribution of dark matter in the Milky Way, because their evolution depends on the gravity, and the gravity is largely set by the dark matter. But excuse me. But roughly speaking, here the idea is that all the stars, excuse me, all the stars in the streams are moving at about the same speed because they all came from the same protogalaxy. And so the proper motion, the motion of those stars, is the resonant feature. And then I can use all the other properties, like the spectra of the stars, to tell me to distinguish those stars from just the stars of the Milky Way. And then I can play the same trick. So my group and other groups have done this. Excuse me. Okay, my group and other groups have done this, and so the top picture here shows it's like a patch of the sky, and it's the stars selected as part of a particular stream called GD1, and using some classical method. And the point is it has a lot of structure, and these classical methods are very good, but the problem is that they require a lot of input. They know a lot about the gravitational potential of the Milky Way, and they also know a lot about the distribution of galaxies that could form streams, which is great. But we also want to be open to other scenarios that these methods don't consider. And so this machine learning method knows none of that, basically. And on this same stream, we can apply the same method, and it finds basically all the same structure, which is amazing, and therefore allows us in sort of a model independent way to be able to find new things in this data set. Okay. All right. So the last thing I want to talk about is a fun community exercise that we did a few years ago, back to collider physics. So in the area of anomaly detection, this is a really exciting topic where there's a lot of new methods that have yet to be really fully vetted on, say, data. And so one of the things that we tried to do, me and some collaborators a few years ago, was to make a data challenge. So we called it the LHC Olympics. The idea was that let's make a data set where we have the contestants, the Olympians. We give them data sets that are like the LHC, and they tell us, is there some new physics in it or not? And we were really worried. The reason we were partly motivated by anomaly detection was, are we blind to new stuff because of the classical way we do searches for new physics? We compress, we pre-specify. And so if we make these black boxes of data sets and we ask the contestants, what is in there? And we were hoping, well, maybe people can develop new methods that will allow us, we're not going to tell them what's in there, just is there something new? And actually we were really surprised in a number of ways by this contest. So by now there's many dozens of methods that have been tested on these data sets, but this was like an early result from the challenge. And I'm not going to say what each of the different acronyms mean, but these are, we injected in this data set a new particle with some particular mass. That's the vertical dashed line. And these different methods show like what the different methods, what these different names are different methods applied to this data set. And there were a few methods that were based on machine learning anomaly detection that actually got pretty close. They said there was something new, and they found that the mass was roughly in the right spot. And then there were other methods that were totally wrong. Like this human neural network was like people, a team of researchers who I will not name, they basically got a bunch of different one-dimensional slices and looked at them by eye to find bumps. And they found a huge bump that was just not a bump. And so that's that. And so this was really motivating, but then actually we made 3 black boxes. I'm not showing the second one. The second one had no new physics in it. And everyone said there was something in it, and they all pointed to the wrong, well, there was no correct answer, so they just kind of pointed in different directions. And the third black box, no one had something and no one found it. And so I think it was sort of like, we were excited that in this first one, new methods were developed that could find the new physics, but on the other hand, there's still a lot of work in this area. So this is just the beginning of the story for sure. And I would say it's a really active area of research, so stay tuned. I think that our ability to find new unforeseen things is really growing dramatically with new methodologies, and we're also starting to see the applications of these tools to real data in colliders and astrophysics and elsewhere. And so, I mean, the amount of data we've basically looked at is really a small fraction of the total, and so this is really exciting direction. Okay, so that basically brings me to the end. Hopefully, there's some time for questions. I think I've hopefully made the case that we need innovative computational techniques to make the data-driven discoveries of the future. Basically, we're throwing away most of the information that's available to us in a huge array of experiments in particle physics, nuclear physics, astrophysics. And it's not just about improving precision. It's really about enabling new science, doing things that were just totally impossible to do before. So anomaly detection is one example, but also there are a whole array of inference tasks that we were basically just scratching the surface of the data. And so now we can do way more than ever before. And I also hope I've stressed that a lot of these methods are being developed by physicists. So we need physicists who have the skills and interests to develop new methods and can connect them with data. So these are like the data physicists of the future, working at the intersection of physics and data science. And this is sort of, they're not theorists, they're not experimentalists. These are really scientists who are trained with statistical tools, but also appreciate and understand the details of experimental data. And with this new cohort of researchers, I think we'll be able to make a lot of progress and make the most of our investment in science over the next many years. Thanks.
Thank you so much, Ben. That was a wonderful, fascinating, and very pedagogical talk. So I'm sure there are lots of questions. So if you have a question, go ahead, type it into the chat or the question and answer dialog box, but I'll maybe kick it off with a question. I'm sure you know the story from 2015, the 750 GeV diphoton excess with gluon fusion producing 2 photons. I guess the explanation, there was a bump, but it was not statistically significant. And I was wondering if we had all the tools back then that we have now, could we have avoided some of this confusion, or would we have been sort of gone through the same process?
Yeah, it's an interesting question. I think on the one hand, we have tools now that allow us to more rapidly scan many things and check. On the other hand, if there's a statistical fluctuation, it's a statistical fluctuation.
Yeah.
I think what we would have found is probably that the events that compose that fluctuations are very much not alike once you look beyond one dimension. So they were all alike in the diphoton invariant mass, but they were not as alike in the other dimensions. And so that would have been easier to do with these tools. On the other hand, if the new physics is sufficiently simple, like say the Higgs boson, in its simplest incarnation, it's literally just 2 photons and nothing else. And now, of course, it's not quite true because there are other production modes and yada yada. But basically, anomaly detection would not have helped that much probably for the discovery of the Higgs boson because it's so simple. On the other hand, if we're not that lucky that it's more complicated, then these tools are really essential, but might be essential.
Okay, thanks so much. Okay, we have a question from Nathan Frank who asks, what specific skills do you see as the most important for a data physicist prior to grad school?
Yeah, I think the most important, which is something that's often missing from our education, is taking basic courses in statistics. Um, I think, especially for physics majors in various places, a lot of places require, for instance, CS, are taking some like computer science courses. And the physics major is often one of the biggest ones. So I don't blame the physics departments for not requiring additional coursework. But I think, in practice, experimentalist day to day, statistics is like the most used tool. And quantum field theory is not is like, day to day, like not the most used tool. And so I would say like, yeah, the core statistical tool, like, taking even basic courses in statistics is essential. A lot of applied machine learning stuff is easier to pick up, I think, in part because it's moving so rapidly. There's a lot of great tools out there. But if you're going to be developing new tools or adapting new tools, having sort of like the foundations, statistical foundations, is really the best, I think.
Great. There's a question from Daniel Lay, who asks, I'm curious about anomaly detection. What methods did researchers use before neural networks became popular, and how well do neural network-based methods compare to them?
And anomaly detection is one of those things where there really wasn't much before. I say neural networks is because it's the most widely used tool, but it also includes other forms of modern machine learning. And there are some nuances about neural networks versus decision trees and other tools. But there's sort of like a matrix of like the tools themselves and how they're used. There were previous works over the last, say, 20 years to do something like anomaly detection, so proto-anomaly detection perhaps, where you compare the data to some simulations of the background in a bunch of different projections. And so if you have a histogram, then I know how to compare. And so if I compare the data to a prediction of the background and they're the same, then I'd say nothing new. If they're different, there's something new. And classically, we do that with histograms. So that's like pretty good, right? And neural networks just allow us to do it instead of just in one dimension at once, in all dimensions all at once. And so the potential there is just, it's pretty dramatic. And so there really is no comparison there. On the other hand, the new tools also allow us to get a better estimate of what the background should be. So if you take your background from simulation directly, that's great, but the anomaly detection often is more sensitive to how good your background's prediction is than if there's anything new. And so these new tools allow us to integrate more information from the data itself, in order to make the predictions more accurate.
Very good. Maybe you can ask a question about how much physics is baked into the machine learning? How much physics-informed machine learning is being used in, for example, your work?
Yeah, there's different ways to answer that question. The first order, as soon as you start training on simulations, physics is used, of course, because the simulation knows about the physics. We told the physics to the simulator, and the simulator then teaches it to the neural network. On the other hand, I think what you're asking is, do we bake the physics in explicitly to the models? And we do a bit of that too. And so sometimes it's more effective. So instead of the neural network having to learn about, say, like, Lorentz invariants, we can just tell it, like, only consider Lorentz invariant functions. And there's usually more upfront work because it's hard to figure out how to specify as a neural network the space of all Lorentz invariant functions. But people know how to do that now. And so we've done a bit of that. And there are also different cases where, like, let's say you have a generative model and you say, like, I want to conserve energy. So you have to, like, then figure out how to, encode conservation of energy into the model. So definitely do a lot of that. And it's kind of a trade-off. Sometimes it's useful, sometimes it's not. It kind of depends. Sometimes you want the model to learn it, and sometimes you want to enforce it explicitly because it's so, like energy conservation, sometimes it's critical that it be exactly true, and sometimes it's fine if it's a little bit not true. Especially in the context of, say, like this example I gave earlier, where you have like detector simulations. Because the resolution of the detector is so large, energy conservation is sometimes less important to be exactly true if it's like swamped by the resolution of the detector. Whereas in other cases, if you don't get that right, you're gonna you'll be totally wrong. And so it just kind of depends on the application.
I had also one last question. I was wondering about the division of labor between AI or ML and human analysis. So is the idea that the AI would get the first crack at the bat, to weed out all all the data, and then the humans would come in to make sure that things, all the interesting things were real, and to check to see if it's a Five Sigma event.
Not exactly. I would say like I don't think AI is going to replace humans in this way. More, I think the goal, like it used to be that people spend a lot of time optimizing, like figuring exactly what the procedure, like instead of like whether you say like, okay, I'm going to look in this region of phase space, and now I'm going to like scan by hand a bunch of different cuts and thresholds and things like that. And now what the researcher will do is specify the problem, and that's where all the thinking goes. Like you specify the problem very, very well. And what is success? How do I get success? How do I validate it? That is where all the work goes. And all the optimization is done automatically. And then, yes, of course, like then, we're going to go in and see what we learned. But if the problem is specified correctly, then the inference part is also part of the specifying. And so ideally that will also be done in a kind of automated way as opposed to being done ad hoc. And so that's where I'm thinking like the new generation of researchers, they will spend less time doing boring things and more time doing fun things, I think, with these tools.
Yeah. Okay, great. So thank you again, Ben, for a wonderful talk and answering questions. Now, for those of you who would like to ask maybe more technical questions after we close up the public portion of this talk, please stick around. Otherwise, let's thank Ben once again for a wonderful talk. I will stop the recording and see everybody next time.